Hello, my name is Matthew Abate, and today I'm going to be speaking about some of the work that we've been conducting in the Georgia Tech Facts Lab and the Georgia Tech Decision and Controls Lab. The title of my presentation today is Improving the Fidelity of Mixed-Monotone Reachable SetApproximations via State Transformations, and this work was advised by Dr. Sam Coogan. This work is motivated by conservatism in the approximation of reachable sets for dynamical systems, and will focus specifically in this talk on the mixed-monotonicity property of dynamical systems, which has been shown to provide efficient over-approximations of reachable sets and has also been demonstrated in real-world safety examples on quadrotors and spacecrafts. A system is mixed monotone when there exists a related decomposition function which separates the system dynamics into increasing and decreasing components, and this decomposition function can then be applied to compute reachable sets as shown on the example on the bottom of the slide. So here there is a system, it's polynomial, it's shown on the upper left. We're going to form a decomposition function for this system. This is shown on the lower left, and then it's this decomposition function that is used to then approximate reachable sets as shown on the right. So in this example, in the figure, the red region, this is your initial set. The dark green region, this is your true reachable set on a time horizon 1 time unit, 1 second. And the shaded green region is the approximation of your reachable set that you achieve when you apply the mixed monotonicity procedure using the decomposition function. And we can see in this example that the shaded green region is not perfect. It's not the true reachable set. Just for starters, it's a hyperrectangle. And in this work, we are going to study conservatism in the approximation of reachable sets, and we'll present some methods for mitigating conservatism. All right, so there are two main contributions of our work. First, we show that conservatism enters the mixed monotonicity procedure in 4 main ways, and we classify and study these forms of conservatism. And our second contribution is that we present 2 methods for reducing conservatism in the approximation of reachable sets using the mixed monotonicity procedure. So these methods are as follows. First, we present a decomposition function analysis-based approach for reducing conservatism, and next, we present an approach for reducing conservatism that relies on defining mixed monotonicity in terms of an alternate partial order on your state space. Okay, so on the bottom, we'll have another example, and this is showing what we are moving towards. So we have a system on your left, and we're showing on the right how reduced conservatism in the approximation of reachable sets looks. And an interesting feature here is that our method for reducing conservatism in the approximation of reachable sets accommodates initial sets that are non-hyperrectangular, or initial sets that are, say, parallelograms or parallelotopes in your state space. And this is interesting and useful because the traditional mixed monotone system tools really only apply to hyperrectangular sets of interest. So there's a slight extension here. So I'm next going to present the definition of mixed monotonicity in continuous time. We're considering a non-deterministic dynamical system given as equation 1, x dot is equal to f of x and w, where here x is your state and w is your disturbance input. And we're going to assume that w evolves non-deterministically inside an interval of possible disturbances that affect your system. Okay, so the system, equation 1, is mixed monotone when there exists a related decomposition function d that satisfies the 5 conditions shown on the bottom of this slide. I won't get too deep into the specifics of what these conditions mean, but just for reference, the first condition ties your decomposition function to your initial dynamics, and conditions 2 through 5, these are derivative conditions on d, and they're going to ensure a monotonicity property is satisfied by a related embedding system constructed from your decomposition function. Okay, so on this slide I'm showing the embedding system. When your system x dot is equal to f of x and w is mixed monotone with respect to d, you can take your decomposition function d and you can use it to construct the embedding system shown here as equation 2. And there are 2 useful properties of your embedding system. So first off, it's a monotone system, and second off, it contains no disturbances. And this is important for reachability analysis, as we'll see in just a moment. Let's look at fact 1. If we consider an initial rectangular subset of the state space, so x dot is equal to f of x and w, and we'll consider an interval of possible initial sets, okay, I can take the endpoints of this interval and construct a state out of them for your embedding system, and then simulate the embedding system forward in time. All right, and the endpoint of this trajectory of your embedding system is then known to provide a hyperrectangular over-approximation of the reachable set of your initial system. Okay, and this is an efficient procedure because all you're doing is simulating a deterministic system forward in time. And this allows you to attain a reachable set for your initial non-deterministic system. All right, so this is a powerful result, and I'm including a reference on the bottom of this slide to a recent tutorial paper on mixed monotonicity. You should all check it out. It's really good. Okay, so we're going to dive right in with our contributions. Our first contribution is to provide a classification of conservatism in the mixed monotonicity property. In particular, we find that conservatism arises in four main ways. So there's type A conservatism. This occurs when a non-tight decomposition function is used in the mixed monotonicity procedure. Type B conservatism occurs when your decomposition function D varies quickly from your vector field F. In other words, in this case, your initial system x dot is equal to f of x and w is far from a monotone system, so to say. There's also type C conservatism, which occurs when your initial set x naught is poorly approximated by a hyperrectangle. And type D conservatism, which is just inherent to the mixed monotonicity property and cannot be mitigated using the theory and tools discussed thus far. Okay, so in this talk, we're mainly going to focus on types B, C, and D conservatism. However, I refer the interested reader to our work where we provide a discussion and some useful results on reducing type A conservatism in the method as well. All right, so the main tool that we are going to use in this presentation to address conservatism in the approximation of reachable sets is that we are going to redefine mixed monotonicity with respect to an alternative partial order on your initial system state space. Okay, so we were given a system x dot is equal to f of x and w. What we can do is choose a transformation matrix, T, a non-singular transformation, and use this to construct transform dynamics. This is equation 4, and importantly, if you take a trajectory of your transform dynamics and in your matrix T, you can backtrack and find a trajectory of your initial system. Okay, this is useful because if you now compute reachable sets using mixed monotonicity on your transformed system, this allows you to construct a parallelotope approximation of reachable sets for your initial system. Okay, and we'll show some examples on the following slide as to how this can be used to reduce conservatism in the approximation of reachable sets. Okay, so now the procedure looks something like this. We're going to start with our system, shown in the upper left, and we're going to also take a transformation matrix arbitrarily chosen here, and we're going to use these to construct transformed dynamics. What we're then going to do is apply the mixed monotonicity procedure to the transformed dynamics. This allows us to compute parallelogram approximations of reachable sets for the initial system. So I'm showing here on the upper right just how forward reachable sets can be computed using this technique, and also backward reachable sets. So the red region is your initial set. The dark green region, this is your time 1 forward reachable set. Excuse me, this is the reachable set that you attain after 1 second. You can apply the mixed monotonicity procedure to get this shaded green parallelotope approximating the reachable set. And then you can also do this in reverse time to get the backward reachable set shown in blue and an approximation of that shown in light blue. Okay, so our observation here is that if you start with an initial set, you can take many different transformations and apply the mixed monotonicity procedure sequentially, and then by taking the intersection of the approximations derived from each approximation, you attain a tighter and tighter approximation of your true reachable set. So this is shown on the bottom. And at this point, you're all probably wondering, so you choose a matrix T. This allows you a parallelotope approximation of your reachable set. Is there a best one? Is there some theory as to how these matrix T should be chosen? And in general, there isn't, but we have found some interesting properties. So for example, it's sometimes a transformation T can be chosen such that your resulting transform dynamics define a monotone system. And why this is interesting is in the monotone case, you get the tightest parallelogram that approximates your reachable set. Okay, so this is shown an example on the bottom of this slide. We have a system. We take a transformation matrix, and what we achieve is a monotone set of transform dynamics. Okay, and then on the right, we see that here, the red dot, this is your initial state or initial set. In the shaded red parallelotope, is the approximation of reachable sets that you achieve when you use this transformation. And because of the fact that we're getting a monotone transform system, we get the parallelotope that touches the true reachable set on all sides. So this is in some ways an optimal transformation. However, you can still choose other transformations, apply the procedure again, and get tighter approximations of reachable sets. So this is just shown using the blue parallelotope. We took a second transformation that was a bit different, and you can still reduce conservatism in the method by considering this transformation and then forming your approximation as the intersection of the two approximations derived from each parallelotope. So this technique of defining mixed monotonicity with respect to alternative partial order on your state space has other applications as well. And I'm just going to quickly show an example here where we're considering a hexagon set of initial conditions and breaking it up into parallelograms, and then using these parallelograms to approximate the reachable set from the initial hexagon. This is an interesting result because the mixed monotonicity procedure has really only ever been used for the approximation of reachable sets from hyperrectangles, and in our work we also do parallelograms, but just from this example you can also see that the more general set of polytope geometries is attainable from this transformation technique. Thank you all for listening to my presentation. I'm going to wrap up quickly. In this work, we study conservatism in the approximation of reachable sets using the mixed monotonicity property. We present two methods for reducing conservatism in the approach. Here, we mainly looked at the alternative partial orders method, but I refer the interested reader to our work for discussion on decomposition function analysis. Thanks for listening. My name is Matthew Abate, and I've included my contact information on the bottom of the slide.